Okay, last time we were doing this, in which we were developing the matrix, and we said that this matrix has like symmetry in it. So we said that, just to revise that, we said that all the diagonal elements are actually the sum of the conductances or the resistances that are attached with the particular node, and the off diagonal elements are negative of the conductance that is connected between adjacent nodes, right? Is it clear? Okay. So then we said that let's try to prove it that what we are writing here is fine or not. Okay. So what I'm trying to do here is try to prove that what we are getting at node 1 is fine or not. So what we have written till now is minus IA plus I1 plus I2 and minus I3 is equals to 0, right? So we have defined our currents. So we will just replace them as we have defined here. Okay. That sounds fine. Okay, so that's what our first row should be, right? So let's compare it with our matrix. So we can see that here we can see that our first row is the same, right? So we have 1 over R1 plus R2 plus R3 that is associated with V1, then minus 1 over R2, and then minus 1 over R3. Right? Sounds good?
Yep.
Okay. Similarly, we can write node 2 or node 3 equations. So let me write it. Node 2. So just remember that, like in terms of matrix, we define that the current is, some of the current is entering the node. Like IA is entering the node, that's why we are taking it as a, like it's as a positive. So if IB is leaving the node, so for that particular definition, it will be negative. But we will write our equation first and then we will try to rearrange it. So at node 2, what should be our KCL? So I think our node 2 should have, 1 minute. So our node 2 should have here I4 minus I5 and minus I2 is equals to 0 because there is no independent current source that is attached to it, right? Okay, so let me write this node 2. I4 minus I5 minus I2 is equals to 0. So then I need to define these currents too. So let's see. I4 is what? V2 over R2. I2 I have already defined. I need to define I5. And what should be I5? Can anybody tell me? Based on its direction.
Should it be negative?
No, I mean in terms of voltage, how I will define it.
Oh.
Is it V3 minus V2 over R5?
Yes, but why I did not take V2, you did not say V2 minus V3 divided by R5.
Because the current's going from V3 to V2 in that direction.
Yes, yes, that's right. Okay, so this helps that if we define currents separately and just plug them in the equation. Okay, so we have I4, I5, and I2 too. Okay, so I'll just plug these values in.
Excuse me, is there any way you could scroll up the page a little bit? I missed some of that under the matrix. Thank you.
Okay. Okay, so is it fine? Okay. Should I go down? Okay, I think I can write it here. Okay. So I4 is minus I5 was V3 minus V2 over R5, and I2 was V1 minus V2 divided by R2 is equals to 0. Okay, then separately I will separate them again. Right? So let's compare it with our equation, okay? So our equation is minus 1 by R2 associated with V1, right? So minus 1 by R2 associated with V1. V2 is 1 over R2 plus R4 plus R5. Okay, so I just forgot 1 over R4. Okay, and then V3 is 1 over R5. That's true, right? So that's how you can see that how our equations are lining up to our matrix, which we have just write it depending upon the, you know, the equations, and we did not try to solve it first. So it's that by seeing it, we analyze the matrix and just write it, okay? So let's try to do add node 3. So let's see that for node 3, we have all the currents or not. So we have I5, we have I3, and we have IB. So it's good. So what should be the equation for V3? Can anybody tell me what should I write?
Minus IB minus I3
Okay.
and I guess also minus I5, but are there no currents entering it?
Yeah, it's okay.
Okay.
We will see. But so the important thing is that, like you did, like if you are thinking that leaving currents are negative, right? Keep that sign convention for all the currents on that node, right? And if you are thinking that entering currents are negative, keep that sign convention here. So when I was writing these node equations or KCL, normally I take entering current as positive and leaving currents as negative. If you see at node 2, I put leaving currents as positive and entering current as negative. It doesn't matter for that particular equation because you are equating it to 0 and your signs will be eventually fine. But just keep that in mind that keep following the same convention for your that particular equation. Okay, but for the matrix, what they have done, like we have written in the matrix, you know, formula here. Where was that? That if you see this, we said that sum of current entering node. That's why we are just taking the leaving one as negative. Okay, so this is that particular definition we are following. But otherwise, I think it should be your call, like whatever is comfortable for you, that what sign you follow. So I normally take it as positive, so it's okay. If I take leaving currents as positive, it doesn't matter because eventually it's equation that is equals to 0, and if you are following the, you know, constant sign convention, so it will end up with the right sign. Okay, so I3, I5. Okay, so it's also connected with our previous, you know, -1 over R3, -1 over, is there a mistake here? Why I write? Can you see a mistake in the equation? This equation is fine, but this equation is not. Yes, go ahead.
V1's is over R3, not R5.
Right, and
Got
V2 was
something got
R5.
messed up.
Yes. So this was R3 and this was R5. So this was R5 and this was R3. Yes. So now if I compare it, it should be the same as the third row. This one. Okay. So you see now that how it is matching with our matrix. And yes. Okay. So, but the important condition is in this scenario was that we were dealing with independent current sources and they were actually connected with only resistor. So there is no voltage source in these circuits, and there is no dependent sources as well. So we need to see whether this system of linear equation or this formula holds up for the what you should say other types of sources as well. Okay, so we will see that too. So for that we are good for now. This is fine. Or is not making sense?
I think it's pretty clear.
Okay.
Yeah, okay for me too.
Okay, so I will start new page. Okay, so I'm thinking to do this example or not. I think let's do it, okay? Okay, 3.2 example. Okay, so okay, so I am doing example 3.2. Okay, and the circuit is okay. Okay, and this is our IB, and this is our IA. Okay, so we have how many nodes we have?
Just a question. What's V2 assigned to?
Yeah, I was also asking. So,
Okay.
no, it's okay. That's a good question actually. So I wrote V2 like this, right? And I can write it like that too. I can draw it like this too. Right? Because this is the same node.
Okay.
Because it's just the wire that is making it a same node. Yes. Okay, so what I was trying to ask, how many nodes are there?
There's 3 reference nodes, but 4 total.
Yes, 4 total, that's fine. 3 non-reference node and 1
And
reference node. Yes, okay.
Okay.
So, okay. Mm. So can we write equation just by seeing the circuit? Or can we write matrix just by seeing the circuit? Let's try, okay? Okay, it's interesting actually. Okay, so first write our currents, okay? So let's try, we will start from node 1, node 2, and node 3. Okay,
What is the thing we're trying to solve in this example?
we are just writing the system of linear equations, okay?
Oh, okay.
We are just writing equations, okay? We're not solving anything here. Okay, what I was saying, can we write equations? So, what will be the current at node 1, independent current source, like the sum of the current that is entering the source, right? So what it will be? As you know, that there is actually what I should say, independent current source that you are seeing that is leaving is IA, right?
Yeah. So is it negative IA?
Yes, I will just write negative IA. For V2, there are 2 current sources you can see, right? So how should I write it?
IA minus IB.
Right. And what should be at V3?
Would that be 0?
Yes, that's true. Okay, so that's good. So V1, V2, V3 will be same. So let's write our admittance matrix. Okay. So node 1, first element, first column is actually the sum of admittances connected at node 1, right? So what it should be? Is it good?
Yes.
Yes. And there is, okay, so can we have admittance that is connected between node 1 and node 2? Everybody's with me here?
No, because it's just the current source.
Yes. But others, do you understand what I'm writing here? Smile, Lamb, Aiden. I'm just trying to.
I understand it. Yeah.
Okay. So there is no admittance that is attached between V1 and V2. Okay. So we will write it here 0. Now, what should I write in the third column? So you know that we are writing about node 1, right? So what should I write in the third?
1 over R1.
Minus 1 over R1,
Minus
right?
it, okay.
Yes.
Why minus again?
Because when we wrote the matrix, it was like this. It was the summation of Gj is equals to 1 n, and then it was summation of minus summation of Gji I is equals to 1 to n. Okay. Should I move back?
No, I can look back on it. I got it.
So if you can see here, this was minus, right? So it was the minus of the admittance connected between two adjacent nodes.
Oh yeah, because okay, it's always negative when it's adjacent nodes.
Yes, like this. Okay. Got it? Okay.
Yeah.
So we will be going here. So about V2. So here, so if you think about think like this, it will be easy. So this is your node 1, this is your node 2, and this is your node 3. This is your node 1. So node 3 and node 1, right? So it's talking about adjacent nodes. So, and if this is node 2 and this is a node 3. So you can say that here, if I'm talking, so this is about node 1 and node 1. So these are about the same nodes. If I'm talking here, so it is about adjacent node, okay? So node 2 between node 2 and node 1, keeping node 2 as a primary node for the second row, I will write here what should I write here? It should be 0, right? Because there is no adjacent resistance or admittance connected between V2 and V1, and all the admittances that are connected at V2 are these, and the conductances or admittances that are connected between V2 and V3 are this. Right? We are good?
That's supposed to be 1 over R3 in the middle, right? Not R2. Plus 1 over R3.
Yes, right.
Okay, just thanks.
Right. So we are good?
Oh,
Anthony?
why do you have node 2 the current in A minus the current in B?
Oh, good. So if you see at node 2 here, so this is our node 2, right? Right? And the independent.
Okay, because they're connected. Okay, you said it before. Sorry. Okay, thank
Got
you.
it?
Yes,
Mhm.
yes. Okay, thank you.
Okay. So what I was asking. So is it good?
In the very middle one, how is R4, when it's 1 over R3 plus 1 over R4, how is that between 2 and also between 2 and 3?
Okay. So if you see here in our equation, in our matrices, we say that this matrix is about, when we are talking about diagonal elements, they talk about all the admittances that are connected at node 2, right? So if you see all the admittances that are connected at node 2 without thinking about any other element, that is 3 and 4, R3 and R4, okay? But when you want to talk about adjacent nodes, so R3 is connected to the reference node, right? And we are not talking about reference node or ground node here. We are talking about adjacent nodes. So that are non-reference nodes. So now if we think about the third element, then we are thinking about V2 and V3. Okay?
Yes, thank you.
Mm-hmm. Okay, so let's write node 3. So you can also look into this, like you can always make relations. So you can see that the diagonal elements are coming like this, because this is node 2 and node 2, node 1 and node 2, 1, and node 3 and node 3. Okay, so node 3 and node 3 should be all the admittances that are connected at node 3. But for the first element, it will be the what you should say, admittance that is connected between node 3 and which node? Chris, Aiden, what should I write in the first element of third row?
-1 over R1.
-1 over R1, that's good. Okay, and similarly, I will write here as V3, V2, -1 over R4, and then 1 over R1 plus 1 over R5 plus 1 over R4. Right? Yes. So that's good. And you can see that this matrix is symmetric because these values are same, this and this value is same, and this value is same. So there is a symmetry in this matrix, okay? But I mean, don't confuse it with the diagonal elements, okay? So I think you should be good when you will be writing and or verifying it with these equations. So we are good about it, okay? And we can just replace the values to find it, the V1, V2, and V3. Another thing we have mentioned, we were just writing the equation, but we were not trying to solve V1, V2, and V3 for 3 by 3 matrix, okay? So in this course, we will not be solving 3 by 3 matrix on paper because it's tedious to do the, what you should say, adjoint, and it's tedious to find out inverse, okay? So here on your book, you can see that there are MATLAB, codes that are given. Have you used MATLAB before?
I
Yeah.
have.
Yeah.
Yeah, briefly.
We took computer science like last year and we had to learn MATLAB too.
Okay. Yeah, so they are not a very, complicated scripts. They are just very, very small and they are already given here. So it should not be a problem to find it out, like the V, okay? So I'm just trying to tell that we are not doing it on paper, like for the unknowns that are V1, V2, and V3. Okay, so now I will move towards the dependent source, and we will see that how dependent source affect system of linear equations, okay? Whether it will keep the matrix symmetric like before or not. So that's what we are talking about now. So, okay. Circuits containing dependent current source. Okay. 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 So this is the circuit we have. We have a dependent source that are beta I naught. It's not a big, rocket science in it that, oh, what will happen now dependent source comes. We always try to go step by step. Okay, so we labeled everything. We are good about it. We know how, to which current dependent source is related to, that is I naught. So we will go with the node 1 equation. Okay, so beta I naught plus V1 over R1 plus V1 minus V2 over R2. Right. Yes. And at node 2 equation will be V2 minus V1 over R2 plus V2 by R3 minus IA is equal to 0. So we are good, right? Okay. And our I naught here is V2 over R3. So we can get rid of one of the thing in the equation 1, that is I naught, by replacing it with V2 over R3. Okay, so yields beta V2 over R3 plus V1 over R1 plus V1 minus V2 over R2 is equal to 0. So rearranging both of the equations, yields. So first I will try to rearrange V1 equation, okay? Or this node 1 equation. So it will be V1 over, or you should go like this, 1 over R1 plus 1 over R2 minus V2 over R2. Okay. V2, 1 over R2 plus beta over R3. No, here should be minus, right? Is equal to 0. Okay? And if I write second node equation, that is this one. Okay. I should do minus V1 over R2 plus V2, 1 over R2 plus 1 over R3 is equal to IA. Right. So we are good about the sign conventions that current is entering the node, and we are good that we are having this positive for the final set of equations. So final set of equations we have are good for making like the matrix and see that whether it works or not, okay? Okay, let's try to make the matrix. Okay, so I will write the equation. First, I will write the current. And then I will write the voltages. And then I will write Okay. I'm saying there is something wrong in the sign. Okay, 1 over R2 and 1 over R2 plus 1 over R3. Okay, I'm not sure what I have done here. Yes, go ahead.
I noticed in the node 2 equation when you first wrote it, I didn't think the signs were right. Because
Okay, let me see. So in the node 2 equation, I wrote V2 minus V1 over R2, right? Okay.
I think that's the first one's negative as well because it's entering.
I am thinking that it should correct its sign itself. It's fine.
Yeah.
No, but there is some problem with the beta thing. Let me see. V2 minus V1 over R2 plus V2 over R3 minus IA. So what I have done here, if you see in this node 2 equation, so I just did not define the currents like normally I do. So I just write the nodal equation, but it should follow the same thing. Okay, let's try to just show you how, if I define the current, how it will be going. Okay, so if this is my I1 and this is my I2, I1, sorry. This is my I1 and this is my I2. So my I1 will be V1 minus V2 over R2, let's say, right? And my I2 is V1 over R1. So if I am writing it at node 1 equation, then it's fine, right? V1 minus V2 over R2. But if I am writing at node 2, I should be writing it as minus I1 plus I naught minus IA, something like this, right? And when I will replace this V1 minus V2, it should correct itself. It should correct it by itself. So this equation is fine, I think. So if I just do it like this, sorry, V1 minus V2 over R2 plus V2 over R3 minus IA, it's okay. So this will become V2 minus V1 over R2 plus V2 over R3 minus IA. You understand what I'm saying?
Yeah, I get
so
that.
This is okay. I think I am getting something I am confused with beta equation, because what I'm doing here at node 1 is beta V2 over R3 plus V1 over R1 plus V1 minus V2. This is good, I think. Right. But how this is matching with the, so that is good, right? Minus into minus. I think there is some mistake in the, or just a minute. Minus 1 over R2.
Should the first matrix?
I think there is a mistake in the book, because our equation is fine, I feel. Because this should be minus inside. See, this should be minus inside. It's good. And this should also be good, because if your beta is positive, you are taking V2 out, your 1 over R2 is positive, and then this is fine. Okay, I think we are good. Okay, so this is the equation. But you can see in this equation, what I'm trying to say, that this is okay, because we are not expecting them to be symmetric, right? These are just the sum of the admittances at that particular node. But here, you can see that our symmetry is disturbed because of this dependent source. This thing, right? Because if you compare with our other matrix, we have the symmetry at off diagonal elements too, right? But we are seeing here that our symmetry has broken due to the dependent source. So it means that we can write by looking at the circuit matrix by ourselves, for the independent current source and the resistors, but we may not be able to write it when there is a dependent source. Okay? Am I clear about that?
Yeah.
Yes.
Okay. So we are good about dependent source, and we are saying that presence of dependent source disturbs symmetry of matrix. Okay, so in this, at least in this scenario, okay. So I think we are good. Now we are talking about another thing, that is writing the nodal equation for the circuit that has voltage sources in it. Okay, so we will talk about it. Okay. Okay. So let's talk about this circuit. So how many nodes are there?
Three.
Okay.
Oh, no, four.
Yes, so there are nodes are 4, non-reference nodes are 3. Okay, we are good. Okay. The interesting scenario here is that if you see here in this equation, in this problem, you are talking about voltage source. You're not talking about current source, right? So you can see that there is an independent voltage source that is connected between your non-reference node and the ground, right? In the case of V1. Ground, right? So can I say that my V1 is 12 volts? Because it's a nodal equation, right? What do you think? So my V1 is 12 volts, right? Why?
No.
Yeah, go ahead.
So yeah, I think so.
Okay. So if there is a current source here, so we can write the KCL. Like KCL says that, okay, we are writing the currents at the node, right? So we can write V1 minus V2, and then V1 minus V3. So that are the current that are entering or leaving. But for the voltage source here, interestingly enough, we have the voltage source between node 1 and node N. So what we can do with this information, we will see. But first we will need to write that there are voltage source we already know, right? So V3 is minus 6 volts. So now I have the 2 node voltages already, right? So I think I will write the voltage, the nodal current of the middle node, okay? So why I am not writing the equation, KCL equation for node 1 and node 3? Because we wrote equations depending upon unknowns, right? So here our unknown is only V2, right? So we need only one equation to solve this problem. We don't need 3 equations to solve this problem, right? So in nodal analysis, we were finding voltages, unknown voltages, right? But in this case, we already have 2 voltages that are at V1 and V3. So we will just write the equation of node 2 to find the voltage at V2. You see what my point is? Or is it not clear?
It's clear.
Mm-hmm. Anyone else? I mean, do you have any question about
Can you just explain again why we can say that V1 is equal to 12 and V3 is equal to -6?
yes. So, okay. So if I write KCL here, let's say I write KCL at node 1, right? So my KCL will be V1 minus V2 divided by 12 kilo ohms, and V1 minus V3 divided by 9 kilo ohms, right? And as we are in KCL, we are defining currents. So we will say it's equal to 0. But we know that our V1 is actually what? 12 volts, right? Because what is normally the voltages? When normally we say VAB, it's the voltage between VA minus VB, right? So here it is V1N, right? The voltage between node 1 and neutral, which will be equal to V1. Am I clear about that? So this voltage is actually V1N, right? Which will be equal to V1 minus Vn is equals to V1, because this is the 0 voltage.
Okay, thank you. That makes sense.
Mm-hmm. We are clear about that? If you have any question in mind, I know there are different type of circuits, and it's hard to process every time a different circuit. Okay, it's okay. It's just, it's not you here alone about that. Every time when we see a circuit, it's different. Okay, but we need to know about different possibilities. So it's okay. But if you have any question and you think it's not making sense, just let me know. We're good about it? Okay. Then we move forward and we find the V2, okay? So we just plug in the values of V2 and V1 and V3 and we will be good. So then our V2 will come as 3/2 volts, and we can find everything else by just putting the values in, because we have V1, V2, and V3. Okay. Okay. And that is also a fair question, that why you are using nodal analysis when you should be using mesh analysis or the loop equation. When you should be writing the loop equation, why you are writing the nodal equation, right? So the answer is that we are trying to see, like, we are picking one method and apply it all kind of scenarios. We are not arguing that this is not the best case for this type of circuit, okay? We are talking about all type of scenarios so that we can understand that method. It's not necessary that this method should be applied for this particular circuit, okay? So yes, you may be right that you should be applying loop analysis here, but maybe it's what you should say, that we want to just learn it, how it will happen with the voltage sources here, okay? Okay, so what will happen if we have voltage source between two adjacent nodes? Right now we have two adjacent non-reference nodes. So now before we were having a voltage source between the node, non-reference node and the reference node, right? So we did not see a case where we have a voltage source between two non-reference nodes. So let's see. Okay. So in this scenario, we have V1, V2, and the neutral node, okay? So for this type of equation, what we normally do, we define what you should say, when we have a node between two non-reference node, when we have a voltage source between two non-reference node, we call it as a supernode. And we will write it as V1 minus V2 is equal to 6 volts, okay? So now we can write it as V1 is equals to V2 plus 6, right? And now if our unknowns were voltages, right? So what should I do? Should I write both nodal equations or should I write one nodal equation?
Would you just write one nodal equation then?
Yes, because we have only one unknown, right? Or you have two unknowns, that V1 and V2 are unknowns. But even if you find one of the equation, then you can find another equation because you already created this equation, right? So this is already an equation. So normally we say that number of equations should be equal to number of unknowns. So there is no use of writing two equations like equation at V1 and V2. We may just write V2 and use this equation to find V1. Am I clear about that?
Yeah.
Okay, so I will write only one equation, but another thing here is, as I have defined this as a super node, right? And this super node is V1 minus V2 is equal to 6 volts. So KCL for the super node will be so this, once I have written this equation, V1 minus V2 is equals to 6 volts, I will take it as a super node, okay? So what this means, I will write it as considering that this is a one node, okay? So I am just writing this as an equation, as a one node equation for that. And I will just replace this. Someone's mic is on. Zachary Hem. Okay. Right, and then we can solve this equation for V2. minus 5 plus 4, yes, and then this will become so B2 solving it will give us 4 volts. Okay, so do you understand this supernode concept or it's not clear? So what we have said that V1 minus V2, we have defined it as a one node. We said it's a 6, and then we write whole equation for the supernode. Okay, so we consider it as the same node, but we did not, make it as what you should say. We did not make V1 as V2, right? We just write the whole equation depending upon that node. Okay. Is it clear?
Yeah.
Okay.
It's not too
So
bad.
yeah, go ahead.
I just said it's not too bad.
Yes, it's not. So there's a story I have particularly related to this subject actually. So when we started this subject, I thought when I was studying this, I thought I was thinking that this was hard. So I never did that before, but I was pre-reading it, like pre-studying it. Before the lecture, I studied the particular topic and go in the class. So once our teacher asked us to solve this circuit, find the equivalent resistance. So that circuit was pretty complicated. And I actually did that before. So I just solved it. And I was like, this is the answer. So the whole class was, what? You did that before? And they were thinking, oh, I know the circuit, but it was actually the pre-studying thing. So, and we found this subject very, very, difficult. So, but I think that if you study it and try to solve it, it will be becoming easy, and just our teacher, there was this one professor who used to say, so every question leaves a black dot on your mind. And if you not try to remove that dot, there will be multiple black dots in your mind, right? So all the time, if you are thinking you have a black dot, try to remove it by asking a question, even if it's a dumb question. Okay?
Okay, yeah, thank you.
Okay, so
Can you scroll up a second? Okay, one second. Okay, thank you.
so I think I will stop here, and we will be doing this, and I have some homeworks and assignments I need to check, and normally I do it on Monday. So I will try to check your assignments, and I will give another homework based on this what you should say chapter, so that it will become more clearer to you. Okay, and the other thing is that I will update the syllabus as well. Okay.
Okay.
Thank you very much. And do you think that there is something like attendance? Because I am actually receiving so many emails about that. So do you do attendance in other lectures too?
No, usually I think the school like has a policy where you can't like grade on attendance, but you can grade on like participation.
Okay.
But I think some students might email the instructor just saying I'm not going to be in class.
Okay. So attendance is not mandatory. That's what you're saying, right?
Yeah, it's not mandatory.
Okay. Okay, because I'm not sure why I am getting so many emails about reporting the attendance on stuff. So yeah, okay.
My one professor has us chat that we're here in the beginning of class because he says there's a strict policy now. I'm not sure.
Yes, it is. We are getting so many emails about that. I'll talk to chairman what it's about.
But yeah, my
Okay.
teacher just calls out her name.
Yeah, it probably changed.
Yeah. Okay. I will see that. Thank you very much for today. And I did not, I think, upload last lecture. I will do that too. And I heard that we should be having the poll for recording the lectures too. So that on paper, we should not have any problems. So I will do that too. Okay.
Okay, thank you.
Thank you very much. Thank you for today.
Have a good weekend.
Good.
Have a good
Bye.
weekend.
Thank you.
Bye.
Thank you.